Alright, so today is introducing the basics of cryptography, symmetric key encryption. So we'll be covering basic cryptographic foundations, talking about why it's used, how it's used, talking about modern cryptography. I'm not going to go too much into the history because why would you need to know the history of cryptography? I don't know. Symmetric cryptography, and the reason that you don't need to know it is because is it secure at all? Okay, using a 40-bit key or something. Is that going to provide any security in 2022? Very little. Okay, so I don't really see a big point in covering it too much. Even legacy technologies. I mean, AES has been around for 20 years. We've got a lot of other encryption methods we can use that are going to be a lot more what we'll be discussing in this class. It's not a history class, so ergo, not a lot of history. All right, symmetric cryptography, go through how it's used, why it's used, that sort of thing, and the cryptographic life cycle. So, the obvious goal of cryptography is to protect data. So, think back to earlier chapters and maybe even earlier classes. What is data? So it's not necessarily information, it's raw points of data. Okay, so that's being like we have a database, it has data in it. Now it becomes information once we process it. So that's the distinction there. And then once we apply that information to make informed decisions, that's when it becomes knowledge. So we're trying to protect data. All right, and there's three major things we're going to talk about here. Confidentiality. Okay, that's the biggest one. So when we talk about the data being confidential, it means it's not going to be accessible to people who it's not intended to be accessible to. All right, so three parts. We talked about these last class, if you remember. At rest means the data is what? It's in long-term storage specifically, right? All right, so generally when we say long-term, are we referring to volatile or non-volatile memory? Non-volatile, exactly, okay? So, which of these three would be referring to volatile? In use, exactly. It's in the memory. Most likely the RAM, although it could certainly be on the NVRAM, and maybe a cache or something like that. But generally speaking, we're talking about RAM for in-use. Now, you can make an argument, well, isn't a page file on non-volatile disk? Yeah, okay. But when you shut the computer down, you're not restoring the old page file contents, are you? Okay, so I would still make the argument that even though it's technically stored on a non-volatile disk with something like page file, even if you want to get into crazy topics like ReadyBoost. You guys familiar with ReadyBoost? So the idea behind ReadyBoost, it's a technology, I think it was introduced in Windows 7. Could have been Vista. But anyway, the concept is that you have an external drive, and you configure Windows to use that external drive as a page file. Okay? So you guys know what a page file is, right? All right. So a page file, of course, is used whenever you don't have enough RAM to hold all the stuff that RAM would usually hold. Okay, so it's going to be installed on non-volatile disks. Okay, so in use, we've talked about in motion. What does in motion mean? It's actively being transported, most likely over which medium? Network, okay? Doesn't have to be network, okay? Don't get caught up thinking that you got to transfer everything over a network. You don't, all right? I think last class, I used the example, what if I'm driving around with a flash drive with a company database on it? Then it's both at rest and in motion, right? It's stored on a non-volatile disk, but it sure is moving, isn't it? All right? So I wouldn't split hairs over that. We could probably debate about that for, the whole class if we wanted. But that doesn't sound very interesting, does it? Okay? I don't think too many people want to hear a debate about at rest versus in motion. So how do we secure data when it's these things? What do we do? If data's at rest, what do we do? Encrypt. If data's in use, what do we do? So we're getting into encrypted memory contents. And I don't think that's really covered in the CISSP textbook, but it's a very important concept, okay? Because like I was talking about last class, you know, if you're using cloud services, which most organizations in 2022 are, okay? Unless you're paying a lot of money for a private cloud, you're on a public cloud. What does that mean? Exactly. So like Ben's saying, you know, you have a physical server. Okay, that physical server may have a half dozen virtual machines, all by different clients. Now, what are the advantages to that? Much cheaper, okay? Because, you know, the virtual machine, you can easily spin up and down the resource requirements, right? Okay. Are there any other advantages to that? So in addition to being less expensive, what else can we think of that would be advantageous? All right, how about just being scalable in general? Okay, because with a private cloud, it is physical hardware. Okay, there is a finite capacity. It is tied to one specific customer. You're not really going to get cost savings with private cloud. Okay, a lot of reasons for that. You might get very slight cost savings if you're a very small company, but for the most part, you're not going to be getting cost savings. But you do get other advantages, okay? Specifically, the advantage of having diversified risk. So you're not just having everything in buildings that you own. Okay, it's in other buildings, presumably separated geographically from you. Okay, is this making sense to everyone? So again, the book doesn't really talk about encrypted memory contents. It's a vital concept, though. Because, you know, let's face it. If you have access to a virtual machine on a piece of hardware, is it that difficult to, you know, take advantage of exploits? No, it's not. Okay? So keep that kind of stuff in mind. Now, let's shift gears a little bit. Let's say we're a data center, okay? And let's say that we're operating at 95% capacity. Okay, that's pretty efficient, right? Let's say that old Intel comes along and says, sorry, we got a vulnerability in our hardware. And to resolve it, you're going to lose 15, 20% performance. Is that a big deal? Why? Yeah, so you had, you know, well-balanced 95% utilization overall. That's great, okay? But it's not great if now you're at 95% and you have to go buy, you know, a lot more capacity. What could you do in that case? Could you sue Intel? I don't know. I'm not a lawyer. My understanding is you can sue pretty much anyone for pretty much anything. There's some exceptions to that, but, you know, for the most part, I believe you could probably take Intel to court. Would it be worth it to take Intel to court? No clue. Okay? You know, it's a topic for a legal class. I would imagine it probably would if you could prove enough damages, though. All right, now Intel's going to try to fight you. And, you know, the good news is that with Intel, you know, you're purchasing from a third party, most likely. So do you have a contract with Intel stating you'll have some arbitration clause or something? Most likely you don't, okay? So imagine if just 500 companies took Intel to court over that. What do you think would happen? Think Intel would go under? It's a lot of legal fees. What do y'all think? I don't either. Anyone got an opinion? So again, I'm not a lawyer. I don't want to speculate too much over the legal system. I'm kind of surprised we didn't see more lawsuits with all those hardware vulnerabilities, to be honest. I kind of expected them. Because, I think they ended up only being a couple percentage different than the original forecast, anywhere from 10 to 30%. But still, 3% for a data center is a big deal. Is it a big deal for an end user? Probably not. Is it a bummer that you lost a little bit of performance? Yeah, bummer, but it's not nearly as big of a deal as it is for a data center. So if you think about it, you have a standard desktop, even a laptop computer, okay? Most of the time, are you hitting 100% across all cores? Seldom, if ever. All right, so if you think about it, you're not hitting 100% anyways. As we know, we can do stuff like turbo boost and all that sort of stuff. AMD has some equivalent too. And we don't have a fixed clock anymore. We may throttle down, we may throttle up. Okay, so for a home user, even a business user, not likely to have a workload that's going to be pinging the CPU 100% of the time. So it didn't really affect home users too much, did it? What about end users? What about, we talked about data centers. You guys see why this is a big deal? So, of course, with hardware, if there's a vulnerability, it's not nearly as easy to fix as a vulnerability with software. All right, integrity. So we've talked about how encryption may be used to protect the confidentiality. What about the integrity, though? Okay, there's a couple different ways it may be used here. Okay, so the first is if file contents are encrypted, it's very difficult, not impossible, but it's very difficult to sort of mess with them, particularly to edit them. Now, you could get into straight up vandalism of the file. That's certainly something you could do pretty easily. But you can't go in and edit something that's encrypted. Okay, not to say that you can't remove parts of it and do other stuff, but actually going into the file, very difficult to do. All right, and beyond that, of course, we have the concept of hashing. Okay, we're going to talk about hashing in a little bit, but the idea here is that we can verify that a file is very likely the file that we intend to have. It's not 100% accurate. We're going to talk about that as well. Okay, so authentication. Obviously, encryption is going to be used here. Okay, because as you know, the basic authentication process, you put in a username and a password. Obviously, the password's not stored in plain text, is it? Okay, we'll talk about that. And then non-repudiation. So non-repudiation being the idea that you can't reasonably deny something that is in fact what it is. All right, and that's played into encryption in a lot of different ways. The main way being we have integrity protections. Okay, we have the ability to compute hashes of files and ensure that they are what we believe they are. That certainly aids quite a bit in non-repudiation. All right, you can encrypt a system log file. Okay, if you encrypt a system log file, it's not going to be messed with, likely, is it? Okay, it's going to help with non-repudiation. Now, if you just have a regular old system log and it's a .text file, is there anything preventing anyone from editing it? I mean, there could be some basic protection measures in place. Let's say that the file itself is just a plain .text, but let's say that the disk is fully encrypted. Okay, does that change things? Maybe. Okay, disk can be fully encrypted. What happens if it's logged in? All right, if it's logged in, that encryption's not doing a whole lot. So it's going to help with non-repudiation. I wouldn't say that it will be the end-all be-all. Okay, it's one aspect of security to discuss. All right, so some basic cryptographic concepts. All right, plain text, that's obviously going to be something unencrypted. Okay, I don't think I need to explain that one too much. Like I said, you got a .txt file. Most likely, that's plain text. All right, so to encrypt, of course, would be the process of performing some encryption algorithm on something. That's pretty straightforward. Okay, ciphertext is going to be encrypted files of some sort. Keys are going to be used to both encrypt and decrypt. Okay, so a public key is only going to be used to encrypt in asymmetric encryption. And of course, a private key is going to be used to decrypt in asymmetric encryption, as well as the private key will also be used to encrypt in symmetric encryption. Okay, we're going to talk more about this as we go. These are just the basic terms. Okay, talking about ciphers a little bit. So the goal of a cipher is to obfuscate the meaning of something. All right, so you got a plain text file. Okay, if you want it to not be plain text, you got to do something like this. So a couple basic ciphers that we're going to talk about. You got transposition. Okay, so transposition, you're changing the order of characters. All right, so you got some sort of a plain text, transpose the characters, change the order around in some fashion that you can, of course, reverse. That's transposition. Now, that contrasts a bit with substitution. All right, so you got substitution cipher. What that's going to do is that's going to, instead of just changing the order, it's going to replace letters. So when I say letters, I should say characters up here because, you know, plain text is not exclusively A through Z, is it? Okay, so that's my mistake. I apologize for that. All right. Now, most likely, you know, and certainly in 2016, in 2022, okay, are we going to just be using a basic transposition as a cipher? Okay, I would hope not. Why? Is it very secure? Okay, it's extremely weak. All right. Let's think back to something like the Enigma machine. You guys familiar with the Enigma machine? All right. So my understanding of the Enigma used both of these. But it had one weakness. Who knows what the weakness of the Enigma was? Okay, so the weakness of the Enigma was when it was doing substitution, okay, it would always substitute the letter with a different letter. Okay, and the obvious problem with that being that you can tell that there's never going to be the actual letter where it is. So that's how that was able to be, quote, cracked. Okay? So does everyone understand that? So, basic ciphers. Now, that's getting into history. We're not going to cover too much of the history. All right, because frankly, you know, I would certainly hope that that's not how our information is secured today. All right, it's incredibly weak. Is it weak by hand? No. But it's weak when we have the ability to perform billions of operations per second. All right, so public encryption algorithms. So of course we know that public encryption, being something, in this context, we're talking about stuff that's open source. Okay, so AES, you can review the AES algorithms if you wanted. Might be a bit complicated, but they're out there. Okay, many, many people have reviewed them. Okay, so the general recommended key size is no smaller than 128-bit. Personally, I say why not go for 256? Okay, because you have a modern CPU, it's going to have processes in place that are going to aid in stuff like AES 256-bit. Okay, so I would just say go ahead and use 256-bit. There's no reason not to. Okay, but the minimum is 128-bit. And in general, you know, when you're doing any sort of encryption, follow the guidelines. Okay, what kind of guidelines would you follow? You're going to follow NIST, National Institute for Standards and Technology, or Science and Technology? I think it's Standards and Technology. Anyway, you're going to follow their guidelines? Probably should. Should you follow your industry regulations? I'm going to say maybe to that one. Okay, because let's face it, a lot of industry regulations are kind of outdated. All right, so there could be a time where we get serious technological advancements and 128-bit is considered inadequate. Okay, just think back to about 15 years ago. Okay, 15 years ago, WEP was considered adequate. Not amazing, but it was considered adequate. Okay, so that's wired equivalent protocol. You guys familiar with that from last class? A very weak key, right? I think it was like 56-bit or something weird. Okay, maybe it was even 40-bit. But that was pretty weak, right? And it's easily cracked, even with not very powerful devices. I guarantee you, for some industry somewhere, maybe if it's even a local regulation, I guarantee you they suggest using WEP. Okay, so should you follow that? I would say not. You may have your own opinion, but in general, regulations are only part of it. All right, you also have to follow the guidelines from practice. All right, so let's face it, practice can certainly get out information a lot quicker than Congress. Okay, not to get political or anything, but I think that's a statement that most people would agree with. All right, a lot of that's by design. Okay, I'm not getting political or anything, but I would say follow guidelines not exclusively from regulation, not exclusively from practice, but consider everything. All right, what else should you consider? Think back to chapter, was it 3, where we did the risk analysis? What else should you consider? Exactly, okay? Think about the finances of everything. Does it make sense to encrypt in 2048 bits? Or let's get crazy, 4096-bit encryption. Does that make sense for most things? Probably not. Well, I say probably not in 2022. If you're watching this video 10 years from now, I don't know what we're going to have. All right? Probably just evolutions of current tech, but maybe we'll have some huge breakthroughs. Who knows? Wouldn't a huge breakthrough be really cool, though? It seems like we've been kind of stagnant on the CPU side. I guess the release of the Zen architecture on AMD sort of pushed the core count and stuff, but look at the IPCs. Haven't changed drastically since 2nd gen I-series, have they? Okay. So you guys familiar with the concept of IPC, right? Instructions per clock, how many instructions can be run on a single cycle. Pretty basic concept. I'd hope you all are familiar with that, okay? But the idea is that, as you add more cores, ceteris paribus, you can do more instructions, but not necessarily more instructions per clock cycle, okay? Same thing with gigahertz. If you speed up the processor, ceteris paribus, usually you see an increase in how many instructions can be performed. But of course, the speed being the clock. Does everyone understand that? Now, there are some exceptions to that, okay? Think about like the bulldozer architecture on AMD. All right, crazy high core counts for 2013, crazy high clock speeds, yet they were slow. Why? There's a lot of reasons. A lot of inefficiencies were involved in that architecture. Certainly had low IPCs, did not scale well at all. It's not a great architecture. Not to state an opinion on AMD as a company, just that particular architecture. So they got behind, okay? Now think about at the same time, what's happened with graphics performance? Okay, not this current generation, but the generation before, excluding that one, I mean, we're getting about 50% on average per generation. That's pretty huge, isn't it? Wouldn't it be cool if we had that on CPU side as well? Okay, imagine where we'd be. That'd be pretty cool. Okay, I think it's pretty cool. So follow the guidelines, but not just one set of guidelines, okay? I'm not here to tell you to follow some regulation written 25 years ago. You know, that will just be silly. All right, so encryption in the enterprise. So obviously, you know, on a home device where it's going to be locked up in your home, it's a lot less of a concern than a corporate device where it may be somewhat accessible to the public. So probably the most important thing here is to encrypt everything that you can. Okay, will you be able to encrypt 100% of things? Never. Okay, can you get pretty close? Absolutely. All right. So if you're rolling out encryption across your enterprise, most likely your enterprise is going to be using something like Windows. Okay, and a lot of your servers are probably going to be some variant of Windows server. Now, obviously, you're going to have a lot of Linux servers as well, but the idea being that most companies primarily going to be a Microsoft sort of focused in terms of what they use for their software. Okay, so Microsoft has I wouldn't say amazing, but it's pretty good for doing an enterprise sort of whole disk encryption solution. And the main advantage with BitLocker, of course, is that it can integrate with Active Directory. Okay, so you can store all of those keys in Active Directory, and that's a secure way to do it. Okay, why is it important that you store keys? Why is that important? Why does it matter to store keys? So exactly, okay. So let's say you have an employee. Let's say that they leave the organization, be it voluntarily or not, and they take the encryption key with them. Okay, so there's a lot of legal remedies you have to that, by the way. So if you were an employee and you decided to leave a company and you didn't want to give them back the passwords, you can get yourself in a lot of legal trouble doing that. Okay, not legal advice or anything. I suggest against it though. But you know, you can have all the legal remedies in the world, and passwords up here. You know, what are you going to do? You can't get that out with an MRI. What are you going to do? All right. So that's why it's important to be able to recover the keys. And of course, BitLocker can do whole disk. It can also do specific files. Basically, whatever you tell it. Okay. It's a reasonably competent application. You know, like I said, it's not perfect, but it's pretty good. Okay, I got home disk up here. So of course, on a Linux file system, we don't have a C drive. We have, you know, sort of a home disk sort of layout deal. Okay, so you can encrypt just the home disk if you wanted. Now there's some disadvantages to that. I think they're pretty obvious. So the main one being, if you have whole disk encryption, you know, you don't have to worry about if it's in your home disk or not. Okay, because the entire disk is encrypted. Okay. That can make it a lot more difficult to do things like surreptitiously install malware. Okay, I think everyone understands that pretty easily. So obviously it encrypts stuff like your databases. Pretty much any modern database server solution you'd be using will easily support several different types of encryption. Okay, I got SMIME or PGP. So the main difference here is PGP, of course, is open source. SMIME, of course, is not open source. And SMIME would most likely be run on an Exchange server, whereas PGP can be used without a server at all. It's really up to you how you do it. And of course, just to clarify, he's talking about email encryption. I think everyone understands that. So I say up here avoid SMS or RCS. Why do I say that? Okay, do I hate Android users? Is that why I say avoid SMS and RCS? Why do I say it? Starts with a U. They're unencrypted. That's exactly right. Okay, so obviously I'm not saying to avoid SMS for everything. What I mean, though, is you avoid it for anything sensitive, okay? Because, let's face it, Do you have a clue where your SMS is routed? I mean, you might have a clue, but you certainly don't know for certain, okay? You can go a lot of places. So if you were to transmit sensitive stuff, it makes a lot more sense to use something like PGP, right? Because that encrypts the entire email. Now, SMIME, I should note, it doesn't have to do encryption of the email. It can just provide a basic certificate. And of course, the purpose of that certificate would be to ensure that it comes from the party that you believe it comes from. Okay? Because the older protocols, so not IMAP, but some of the older mail protocols, you can edit the header in the packet before the email goes out. And when you edit that header, you can put whatever email address it's from that you'd like to. Okay, does that make sense? So you can't do that with IMAP, but you can do that with, I think, POP, but don't quote me on that. But just understand it's one of the older you can do that with. All right. So symmetric encryption. You have one key. It's used to both encrypt and decrypt a file. All right. So you got plain text. That's represented by the P. You got cipher. That's represented by our ciphertext. That's represented by the C. All right. So the idea here is you have a single secret key that's used to both encrypt and decrypt. Is everyone clear on that? So asymmetric, of course, you have a public key that is used to encrypt, and you have a private key that is used to decrypt. Ceteris paribus, this is a slower approach. It's also a more complicated approach, but it has a lot of advantages. Okay, so there's a lot of people, particularly in the security research practitioners, who will post their PGP key. Okay, and obviously they're not posting their private key, but they post their public key so that you can encrypt your messages using the public key and send it to them. Okay, and that's the main advantage. Okay, you have one public key, you can share it with anybody. All right, so you can post it anywhere. Most likely, though, you're going to end up, if this is implemented across an organization, most likely that's going to be stored on whatever mail server platform they're using, be it Exchange, be it Office 365. It supports that storage, okay? And that makes it a seamless process. PGP can be kind of complicated, okay? SMIME's a lot easier in most cases. But both of them can integrate with Outlook and, I would say, most good email clients. Not mobile email clients, but desktop email clients. So that's certainly something you could do. Of course, PGP can also be operated through the command line or through terminal, okay? And that may be an approach that some people may find a little bit easier to work with, okay? Who uses a mail client in here on their desktop? And when I say desktop, I don't necessarily mean a desktop, I mean a non-mobile device. So laptops would still be included here. Who uses one? So just a handful of people, okay? So integrating this with webmail, you'd probably end up using either command line or terminal. It's not necessarily hard to do once you've done it a few times, but that's what we're talking about here. All right, so basically it's just showing you the advantages of using asymmetric encryption. So the idea here is that if you have one person that you're sharing with, you would basically have one private key for the two of you, okay? And this is assuming that you're not going to be repeating any private keys. Does that make sense? So as you move up here, you have 3. So person 1 and person 2 share a private key, and then person 2 and person 3 would share a private key, and person 1 and person 3 would share a private key, which has a total of 3. All right. I'm not going to go through these up to 1,000, okay? We could be talking about that for weeks. But you get the idea. All right, I hope you get the idea. Do you get the idea? Okay, so the idea is that every party that they're interacting with would have a unique symmetric key. Now, I contrast with asymmetric. Okay, so asymmetric, you have a public and a private key. That's true, but you know, basically you have that for everyone. You can use the same public key with everyone. It's perfectly safe. Well, I wouldn't say perfectly safe. Okay, because is anything truly perfectly safe? Not really. I don't mean to get too philosophical, but you know, it's sort of a lofty goal. All right, so basically this is just saying that each person has their own public and private key, and it becomes a lot more scalable. Okay, is it feasible for an organization to manage 500,000 keys if there are 1,000 employees? Not easily. I wouldn't say it's impossible, but isn't it a lot easier if people just manage their own keys? I think so. All right, so hashing, we talked about this. The concept is that you're verifying the integrity of a file most of the time. You can, of course, also use this for a lot of different things. But generally speaking, its primary purpose is to verify the integrity of a file. So most likely, this is going to be used when you're downloading something. I have up here a Linux distro. Maybe you want to try out a new distro. So, of course, you can verify the contents of it. That's built in to, I think it's built into PowerShell on Windows. It's a lot easier on Linux and Mac, of course, but I believe it's also built into PowerShell. I think that was in one of the Windows 10 updates. I don't think it was in there in the original release. I don't think it's in 7 or anything like that either. So, but the problem with this is collisions. All right, so a collision occurs whenever the hashing algorithm detects that two files, or I wouldn't say they detect, but they produce the same hash. Okay, and this comes into some pretty substantial problems, all right? You guys follow the Apple CISM controversy? Okay, did anyone follow it? So basically what happened is that Apple announced that they were going to be doing local scans for CISM content, which is, of course, child expletive material. All right, I don't think I need to go into details about that. And that was going to be done on device prior to upload to iCloud. Okay, and there was a big controversy surrounding that for several reasons, one of which was collisions. Okay, so they were getting the database of hashes from I think it's like the National, I don't remember the exact acronym, but it's some quasi-governmental agency that collects images and hashes them. Okay, and the problem is they were getting a lot of collisions. Okay, well that wasn't the only problem, that was one of the problems. All right, so there'd be a perfectly innocent picture of, say, a dog, and it would generate the same hash as explicit material. Okay, does that make sense? And that was one of the controversies. Now, another controversy is that's happening on device. So even though it's technically just hashing, there's a lot of privacy concerns with that. Okay, so right now they're just using it for CISM. Okay, can you envision a potential scenario in which a government, not necessarily your own, although it could be your own, may want to add some hashes to that are looking at things like the picture of the Tank Man. Okay, you guys familiar with the Tank Man, right? From the Tiananmen Square 1989 protest? Yeah. Can you see that happening? It could. I'm not saying it will. I'm not stating an opinion. I'm just saying that's another potential concern here. Okay, so should Apple do that? I don't know. I mean, I have my own opinion, actually, but I'm not telling you what my opinion is of it. I'm saying that's a big controversy with hashing. Another controversy. You guys remember what SourceForge was doing? Okay, so SourceForge was being a little bit ridiculous. Okay, so they had, you guys familiar with SourceForge, right? They host a lot of software. And they used to host a lot of open source projects until they screwed up pretty royally. And what they were doing was they were calculating the hashes based on what was actively on their server. Okay, so this came into play when they began to add in adware to various projects they were hosting. Okay, and the hashes were matching what was originally uploaded by the actual creators or developers. So that obviously causes a lot of problems, right? Okay, and I believe at one point they were also actively hosting malware. Don't quote me on that part, but yeah, it's not best practice to have a hash automatically update because a file updates. That should probably be something done manually. Does that make sense? All right, cryptographic modes of operation. We're not going to cover these too much, but I'll just go through them kind of quickly. You have electronic code book mode. And basically what this does is takes 64 bits of data, sort of divvies it up, kind of like the process of forming a packet. And it encrypts those blocks using the same key every time. Now, the obvious downside is, if you have the same 64-bit block, you're going to know, because it'll be the same output, right? Does everyone understand that? So obviously all the others address those vulnerabilities. We have cipher block chaining mode, where it uses an exclusive OR operation, which of course, exclusive OR just referring to the fact that if either are true, it's a 1. If both are true, it's a 0. Or if both are false, it's also a 0. It's just doing that operation on blocks of the data, and it's more secure. And cipher feedback, that's basically just real-time cipher block chaining. So real-time, it's mostly used for stuff like streaming and any real-time operation. Lots of different real-time operations. So we have output feedback mode. Okay, that's basically just using the feedback mode with a seed. Okay, so you guys remember the concept of a seed, right? Okay, I'm not talking about something you plant in the ground. I'm talking about something that is going to be used for, quote, randomization. And the idea here is if you have a seed number, it's going to be the same if you run it with a particular seed. Okay, so you can change that seed. And that's what it adds, basically. You got counter mode. It's basically just adding a counter, which of course is going to be an incrementing counter. So that's going to help randomize things a little bit. And then of course you have Galosis counter mode. Okay, that's going to be basically just adding in the verification process to make sure that nothing was corrupted or anything. So like I said, I'm not going to cover those in a lot of detail. Just understand the basics of them. All right, data encryption standard, 1977. That's why I have the old man emoji. That's pretty old, right? So this is using a 64-bit cipher, and in most context, or I would say in every context actually, it's going to be superseded by more modern standards like AES. Okay, it's a very weak algorithm. I mean, come on, 77. You know, what was going on in 77? You know, I don't even think I mean, we certainly didn't have Microsoft Windows. I think that was the 80s, but I'm not even sure that we had a lot of DOS development at that point. So definitely a long time ago, right? I mean, can you guys believe that's getting up to 50 years almost? So yeah, wouldn't use it for anything modern. So of course you have the international data encryption algorithm. It's going to be more secure than DEF, of course, using 64-bit ciphers. And most of these are going to be using 64-bit ciphers, by the way. There's only a few that don't. But this uses 128-bit keys, which are adequately secure. And it's used in PGP. So if you ever use PGP, which I encourage you to try out, you know, you're probably using IDEA. All right, then you got Blowfish. Kind of a funny name. I don't really know where the name came from. But the idea here is that it's a faster algorithm, and it also supports pretty large keys. It's not the largest key in the world, but 448-bit is not small by any means. Okay. Now, when I say faster, obviously that's ceteris paribus. Okay. There may be some context which is actually slower. If you're using a 448-bit key versus a 64-bit key, obviously which one's going to be faster? 64-bit, okay? But if you have the same size key and you're comparing algorithms, it's a fairly fast one. Although we'll talk about AES in a little bit, and that will, of course, be, I guess I duplicated that slide, okay? So skipjack, this is a funny one to talk about. It's one that the government came up with. They kind of thought everyone would implement it for some reason. I don't want to get political or anything, but anyway. The idea here is that it uses an 80-bit key, which is below, and this is, by the way, the 90s. So it uses an 80-bit key, and that's pretty weak by itself, but my favorite part is that it has the ability to escrow encryption keys. And of course, escrow means to recover them, basically. And that escrow is held jointly by the U.S. Treasury and NIST. Okay, so law enforcement can go, and with a warrant, they can go approach those two agencies, and they can get any key they want. Okay, so I would recommend against skipjack for anything. Okay, a lot of reasons for that. You know, the 80-bit key is bad enough, but this one right here, does anyone disagree? Like, it's okay if you disagree, but I just don't see why. I mean, that's all I'm going to say there. All right, so a much better standard would be advanced encryption. So this has 3 different options for the cipher and the key. So depending on what size cipher you're using, or actually depending on what size key you're using, I mean, you can adjust the size of the cipher. So you can either do 128-bit, 192, or 256-bit. Now, what do I recommend? 256-bit. Okay, why not? But, you know, it really depends on what processor you're using. Let's say for whatever reason, you're using a Core 2 Duo. Okay, so does a Core 2 Duo have, does it have stuff built into it to help with AES? No. Okay, so in that context, you would probably stick to a smaller key, because 256-bit on a Core 2 Duo would be pretty miserable. But it's either, I think, 2nd or 3rd gen I-series where they introduced it into the architecture to have AES where it's going to be handled not necessarily by the CPU, but by part of the CPU. And in that context, 256-bit will be almost instantaneous. All right, does everyone understand that? So it's going to depend on what hardware you're using. All right, symmetric key distribution. Okay, as you know, with a symmetric key, both the sender and the receiver have to have it, right? Okay, so if they both have to have it, that means that they have to get it in some way. And this is where it becomes kind of problematic. Okay, because how do you inform someone of a key? You know, do you walk up to them with it on a piece of paper? You can. What if that person's across the country? Then what do you do? A lot of different ways you could. Certainly you could do a lot of things. But there's 3 primary ways that you can actually exchange symmetric keys. Okay? Offline, we just talked about, you know, you meet up with a person somewhere. You probably shouldn't do this on a phone call if it's something sensitive, okay, because are phone calls that secure? Not really. Okay, if someone wanted to, they could listen in. I'm not saying that it would happen, I'm saying it could happen. All right. So, of course, you can do a public key exchange where you post the public key, verify the identity across the public key, and then exchange your private key, and then hop on the private key. That's kind of convoluted, to be honest. At that point, why not just use asymmetric encryption? Okay, that's what I don't understand. Because hypothetically, you send it with something via like PGP or something, and then just, you know, then hop on the private key symmetric. But anyway, you get the idea. Okay. Diffie-Hellman, we're going to talk about that next class. All right, but the idea is that it's an algorithm used to exchange keys. So those are the primary ways to distribute the keys. Just kind of wrap things up. Talked about cryptographic foundation. Talked about modern cryptography. Talked about symmetric cryptography. Next class, we're going to cover a lot more with asymmetric and some other specific concepts. And we also covered cryptographic lifecycle. Any questions? All right, see you all next class. Have a good one.